Yay. Well, here it is. What we've all been waiting for. Me for the longest. Sorry about the... It's a bit off. Yeah, got the board now. Yeah. Right, so, a whole new series. I did mention it in one of the videos, but this is the one where I'll be doing computer science stuff. Mainly one project that I've wanted to do, but it's just based around like logic gates and stuff, which is why I have this. If you don't know, the basic logic gates look like this. So this is, it's just, basically it's a representation of a wire. I mean, I know these bits are representations of a wire, these little stick bits, but what goes in here comes out here. It's basically the null gate, so it changes nothing. This is a not gate, so if a 1 goes in here, that's 1. If a 1 goes in the front of here, then a 0 comes out, because it inverts it, and if a 0 went in, then that would be a 1. You get the idea. This is an AND gate, so both of these inputs have to be 1 for it to output anything, and this is an OR gate, so only one of its outputs needs to be 1 for it to activate. And those are the basic things that you can do. And then there are more complicated gates which are made out of bits of these gates, but it'll be, well, it won't be easier, but it will be more fun to show you in this medium. Right, okay, so here we are in Minecraft. It's a fun medium. Welcome to Procrastination Land, if I can fly. Okay. I made lots of things. Those did have like leaves and stuff on them, but they appear to have disappeared, which is fun. But this is the main thing that I wanted to talk about, because these are the same gates. So this is a this is how a transistor works. All these gates are made up of transistors. They're like the base component that you can put them in. So what this does is there's a permanently on source, and when you apply a current to it, it turns on. An easier way of representing it, which isn't this, is just a line. It's just when you power it, it powers something else. So this is an OR gate, so that's the last one on the board that you just saw. So it doesn't matter which one of these is on, that will always be on as long as it's one of them. This is an AND gate, so both of these have to be on for the lamp to turn on. And this is a NOT gate, so if it's on, then that's off. This is an example of something that you can do. You can see some of the gates here. This is an AND gate, this section here. This is a NOT gate on there. And when you put it together, what you get is, if one of them is on, then it's on. If both of them are on, then it's off. And yeah, if neither of them are on, then it isn't either. This is an inflated way of showing the process of an XOR gate. And that means that the inputs... Hang on, I'll show you on the whiteboard. Okay, so an XOR gate, the symbol looks like... the symbol looks like that. So it's the same as an OR gate, but it's got this little thing here, which essentially means the not part. A handy little tool is a trace table. So you have your inputs, since we have multiple inputs. Hang on. Since we have multiple inputs, we'll have multiple columns. So with this one being A, which we can assign that one, this one being B, which we can assign that one, and that being P, row, whatever you want. Usually it's P for some reason. Your guess is as good as mine. Unless you want to Google it, then your Google is better than mine, because I didn't. So what this does, this trace table here, it gives you all of the possible inputs. So A could be 0, B could be 0, A could be 0, B could be 1, and that just... So this is all the possible combinations, these 4 lines of possible inputs, and that's how a trace table works. And then in this column, you put what B would be as the output. So as we saw, it's 0 if the inputs are 0, 1 if one of them is 0, but if one of them is 1, then the output is 1, but if both of them are 1, then it's 0. So this is just an easy way of looking through your program and looking at every single possible input and then working out what the output would be for each of the things. And this is a lovely representation of computer science and logic gates stuff. So this is the gate that you just saw. It's written like this. So XOR. It stands for exclusionary OR. So if one of them is, well, the input has to be the sole input for it to produce an output, essentially. And then that thing you just saw is a massively, I mean, it's not overcomplicated, but it's over-represented in the difficulty that it needs to be. So I'll just show you some other ways of building that. Right, so we're back here. This is the first way that you can build that behemoth differently. So this has the same thing, so if just one of them is on, both of them turns it off. So what's going on here is this is an AND gate, this yellow block here, and these are, yeah, it just works. So this AND gate runs through here, and it changes the configuration of this torch to make it on or off. Then this AND gate needs to be switched. If this AND gate is switched off, so if both of them are on, then that powers, but it keeps these redstone torches unpowered, so it can't power the redstone dust and turn the lamp on. If one of them is off, then this AND gate produces an output. So this torch turns off, so it doesn't affect this one. It doesn't turn this on, which means that the redstone torch can be on, then you get redstone and an output. This is something I looked up online because, well, that's my own one over there. But yeah, this is a compact way to do it. So it's, the footprint is 3 by 4 by 2 deep, because you have that one, that row, and then these are the output rows, but there are still components that you need, these torches. So that is a complete cubic area, not cubic, rectangular area, cuboidular, something like that, area of 24. This one is slightly bigger than 24. This is my own one, which I made from, which I made from this. which is 3 by 3 by 2. So this is 18 area, volume, so it's slightly smaller than that one, and it runs on the same principle where these have that, and there you go, just in there's a redstone torch, so that acts as the AND gate, which changes these two redstone dusts, and then if that's off, then this one becomes unpowered, and it can power it in there. So this is slightly smaller. However, slightly embarrassing, there is an exceptionally small version, which is this. These are a wonderful little component. They're called comparators, if you haven't seen one before. What this does, because it's in subtract mode, with the little light on, when you put that on, it gives a 15, the redstone dust gives a range from 15 if it's really close to the power source, down to 1 if it's 15 blocks away. So what this is doing is it's putting 15 in here, 15 over here, and because 15 minus 15 is 0, it's not outputting anything, which is why these are turned off. However, this one isn't outputting because this isn't turned on, but there's a 14 in here, so it's being powered. So it powers this block, which is why that redstone dust is on, which turns the lamp on. If you do that, it's just a mirrored thing, so it's exactly the same. So by turning that one on, that one now becomes on. If you turn both of them on, then they're both giving 15 in and 15 subtract, which is 0. So they're both 0, and you get no output. And this is 1 by 8 by 2, 1 by 4 by 2, which is a volume of 8. So that's over half the volume of this one. So yeah, this is great. I'm going to be using this a lot. I'll just set up a model for the redstone dust limit, so the 1 to 15 thing. Okay, so here's the model. This is the power source, so this could be a lever or a redstone torch or a redstone block. This is 15 blocks long, the red things each 5. So this right here is on a value of 15, so that's the most it can be. Then this is each jump down, so that's 14, 13, 12, that's 11. Then that's 10, 9, 8, 7, 6, this one's on 6, 5, 4, 3, 2, and 1. This is the last one where you have an output. So if we stick a redstone lamp here, that one turns on, so that's the last one. However, this one isn't, so that's a value of 1, that's a value of 0. This allows for some interesting coding things, which I'll show you in a future bit, because you can have coders depending on the strength of this. So if it's, say, a signal strength of 4, then that could tell you something different to a signal strength of 12 up here. So yeah, that's the basic introduction to the Minecraft, the coding side, all that jazz. But yeah, that's quite good. This is just sort of an introduction thing for all of the different logic gates, all of the symbols and names for all of the things. This is the example of how you can combine all of those logic gates to make a different logic gate, which can be represented as one of these. Tiny little thing, smaller than some of these actually. And how all of these can be made up of simple transistors. Ah, wait, no, I didn't show you that, did I? Okay, back to the board. Okay, so what you have in a transistor, just the, yeah, you have your current going in, then it connects here to a plate, and then that's the current going out. So that's the in, that's the out. Then you have another wire running across here. Well, this is all a circuit diagram. So you have another wire here, which is your power. I mean, you could call it whatever you want. In diagram, it's called, I don't know, I can't read that. Oh, the base. So this is the base. That's the input, that's the output. What happens is there's always a current running through here, and this base, that line there, doesn't allow that current to pass through unless the base, which is the binary input of 1 or 0, if that's 0, which it currently is, then it doesn't allow the current to pass through the base. However, if this is powered, then this current here, not that current, this one, runs along the base, because it's now conductive, and then comes out as the output. So this is a transistor. This is what depends the state, but this is always on. So an interesting thing you can do with this is chain them together to form those logic gates, which looks like this. So this is a representation of an OR gate using transistors. So you have your in and your out. These are your two, well, this is always powered. So these are your two inputs. You don't have two inputs over here, it's these on the transistor. So if this, well, essentially, this charge here can go down this path or this path. So it doesn't matter if this is a 0, as long as that's a 1, because it still it can't go down this path, but it does still have this path that it can go down, and that is now a 1. That's O for output, or 0. So as long as at least one of these paths is free, you can still get the current out the back. For an AND gate, it's slightly different. Instead of being in parallel, so you have one there, and then it connects. Those are in parallel because they're parallel connections, so you can travel down either of them. However, these transistors are placed in series, which means that even if this one is a 1, so the charge can go down here, this transistor also needs to have a 1 in it to allow the charge to pass all the way through to the output. And yeah, knots are really annoying, but yeah. There are some photos that I'll put up right at the end and do some voiceover stuff for things on a program called Logically, which allows you to make things out of logic gates, which is really cool. That's actually how I got inspired to do this, because I just had so much fun, because in college you get free periods, and I just had so much fun messing around with it during my free periods. Well, currently, at the moment, my profile picture for this channel is one of the things that I made in Logically. It's a two-digit display, I think. Yes, two-digit display made out of logic gates and like lamp things. It was really cool. But yeah. So this is an AND gate. That's how it works. This is called series because they run serially. So one comes before the other. Whereas in parallel, you don't have to, one doesn't rely on the other. So yeah, I'll show you those photos now. Okay, so this is the transistor I just showed you. So this is always has an input of 1, and then it's by turning this switch, or giving it a 0 or 1 input, you could imagine, this light turns on, like that, but only if that is powered, on the inside. This is there we go. this is an AND gate, so this is the two transistors in series, as I just showed you, where the inputs are from the switches. Ignore that. This is a NOT gate, so this uses an XOR gate and one continuous input and one positive input. So this will always run 1 when the input is 0, but when you turn that on, the XOR gate has two positive inputs, so it becomes negative on the outside. OR gate, there we go. You don't need this bus here, it's just for having multiple inputs into one output. But these are the two transistors here. As you can see, they're running in parallel. There are some other examples of things that you can do with these gates. This is a latch, so at the moment, when you press this bottom button down here, this will send a trigger to here, this latch, this OR gate right at the bottom, which will send an output to the bottom lamp. It will also turn this top NOT gate to give a 0 output, which turns off this OR gate. So it turns off the lamp, and then the NOT gate on the right turns on. So when you release the button, it allows the OR gate to stay on, and it just flips between the lamps. If you press the same one twice in a row, it won't do anything, because it already has a positive input. But yeah, that's an example of something you could do. These are the more complicated ones. So this one, third from the top, the XOR gate, that's what I just showed you. So how this is run is, at the top you have one output with the actual gate, so its representation. This is what the XOR gate looks like, as I showed you. The NOR gate above it, and the NAND gate above that, and the XNOR gate is funky. But yeah, it's essentially just an XOR gate with a NOT on it. The NOR gate is an OR gate with a NOT on it, and a NAND gate is an AND gate with a NOT on it. So these are all of the inputs. No, these are all the possible gates. Well, they're not. They're like the second level of gates. And on the right, those are all the inputs. So, as you saw on the trace table, when you have, so these are the two inputs, they can be on or off. As I showed you, so this is the output column. So when it's 0, 0, it's 1 for the NAND gate, and it's 1s all the way until you have two positive inputs. The NOR gate will only turn on when both are 0. It showed you the XOR gate, and then the XNOR gate is just the opposite of that. That is far too complicated for me to explain. This is the start of a counter, which produces a binary output. So the top lamp will be the 1 column, the bottom lamp would be the 2 column. If both of them were on, it would have meant that the button would have been pressed 3 times. And that's the end of the stuff that you're going to see today. I think I'm coming down with something. I've got a little bit of a sore throat, so the quality of the dictation may not be very good. Yeah, sorry for that. But yeah, that's it. It should be less than, I'm not going to say it's going to be less than 20 minutes, but it should be somewhere around 20 minutes, this video. Yeah, that's the first half of the setup. Bye, and I hope you're as excited at me as blah blah. I hope you're as excited as I am about the board. There we go. I'm going to blame that on the fact that I'm feeling a little bit ill, and not the fact that I can't speak. So, bye. Yeah. Ciao, mi compadres.